Yeah. Can you see the screen?
Yes, sir.
Okay. So the argument is like this, right? So if I say a is greater than 0, and I say a is less than epsilon for every epsilon greater than 0, what can you say about a? A greater than or equal to epsilon 0, but a is less than epsilon for every epsilon greater than 0. So what can you say about a?
A
A
equals
cannot be
to 0.
minus 0.1 or whatever, right? So it cannot be negative, right?
A equals
If
to 0.
yeah, it's a equal to 0. That's the kind of argument that they are making there also. Whenever I say it's less than epsilon for every epsilon greater than 0, it's true for the equality as well.
Yes, sir. Okay, sir.
Okay. Yeah. Okay. So any other questions?
Yes, sir.
Ah.
Sir, I have a doubt in sir expectation calculation of the expectation. Suppose x is a non-negative random variable,
Mhm.
and for that the expectation of x is for something discrete x into px of x. No, sir.
Correct. Summation.
Summation of that. But
Correct.
sir, one more way they have defined that it is just an integration of the distribution
Correct.
function d of fx of x. Sorry, f complement. So sir,
Correct.
how can I relate these two things, sir? Actually, I'm
Okay,
not
so
getting the
maybe,
second one.
yeah, we will do that. Okay, now. Okay, so let's start with that. So
Okay, sir.
let you take x to be positive. Okay, so let's assume x is discrete. I'll do it for discrete. I'll leave continuous as an exercise. Okay,
Okay,
discrete,
sir.
non-negative, random variable, taking values in, let's say 0, 1, 2, etc. Okay, is this fine? It doesn't matter, it should be countable, that's all. Okay, if you want to keep it general,
Yes.
I'll do this. Okay, so maybe I'll just write a0, a1, etc. Okay, which belongs to R. Is that fine?
Yes, sir.
Okay, with PMF, probability mass function, let's say px of x belongs to this set, right? Okay, now what is the expected value of x? This is summation overall. Let
X.
me let me call this set as script A. Okay, so all x belonging to script A, x px of x. Do you agree?
Yes, sir.
Okay, I'll expand this. I'll expand it as follows. Okay. Okay, maybe okay, I'll try this for A naught. Okay, so this will be A naught. Okay, Px of A naught plus A1 Px of A1 plus etc. Right? Is that fine?
Yes, sir.
Okay. So now, what is it that I'm saying? I'm saying A naught times Px of A naught plus A1. So definitely A1 is greater than A naught, right? This is greater than A2 and so on, right? Okay,
Yes,
I'll
sir.
just
We
write
can.
it. Let's assume that A0 is less than A1 is less than and so on. Okay, this is an increasing thing, right? So now, what is it that I can do? I can do the following, right? I can order them in a different way. So I have to basically, okay, need to show. I'll write this so that you will see what needs to be done. So that the above is same as what? Summation for all x belonging to A, probability of x greater than x, right?
Yes, sir.
Is that fine? Okay, so what is this? This is the first term will be probability of x greater than, well, in this case, let's assume that it's greater than or equal to, okay? So this will be greater than or equal to A naught
A naught.
plus probability of x greater than or equal to A1 and so on. Okay, is that fine?
Yes, sir.
So now can you stare these two and tell me whether they are equal or not? what is this? This is sum over all x belonging to A, right? Because it's A naught. Probability, okay, Px of x. Do you agree? Do you agree with this? What is this? This is summation from x equal to A1 to infinity Px of x, right? And so on. So now when you add them, what do you get?
Same sir, expectation of x only.
So that, yeah, so can you see that these two are same?
Yes sir.
Okay, so
Yes.
let's look at a specific example. Suppose A0 equal to 0, A1 equal to 1, and so on. What will happen to this? This thing? This will be what? A0 PA of 0 plus A1 PA of PX of 1, okay, and so on, right?
Yes.
What will happen to this? This will be summation over all x Px of x. There will be Px of 0, Px of 1, Px of 2, and so on. So let's write this. This will be Px of 0 plus 1 times. Okay, A0 will not occur because A0 is 0, right? This will be A1 is P1, 1. So 1 times Px of 1 plus 2 times Px of 2 plus 3 times Px of 3 and so on, right? So for this special case, you can see that I can write this as what? Px of 1 plus Px of 1 plus and so on, okay? What am I doing? I'm taking Px of 1 here, okay? Sorry, not 1. Px of 2 plus and so on, okay? I'm going to take 1 Px of 2 from here and 1 Px of 3 from here and so on, right? That will give me this. Yes. There were, if you look at this, sorry, I'm going back and forth. So this is 2 times Px of 2. I have P, that is nothing but Px of 2 plus Px of 2. So I have already taken 1 Px of 2. I will take the other one here. Okay, Px of 2. The third one has 3, so I'll take 1 here. Okay, and so on. Now in the next case, Px of 2, I only had 2, so I have exhausted that here and here. So I'll take Px of 3 plus Px of 4 plus and so on, right? So this is nothing but, what is this? Px of 1 plus Px of 2 and so on. This is nothing but probability of x greater than or equal to 1. What will be the next one? Probability of x greater than or equal to 2 and so on. Is that fine?
Yes sir.
Yeah, so now for a non-negative random variable also, you can show that, but the only thing is, the question is, how do you show that, right? See, I can write, so if you can show for discrete, then continuous is quite straightforward. I'll leave it as an exercise. Think about it, okay?
Okay sir.
Is that fine? Okay. Did I answer your question or no?
Yes sir.
The other way to look at this is, if you look at integral of probability of x greater than t dt, so that you should somehow show that for a small interval, it's x times fx of x dx, right? Yeah. Okay, so any other questions? No? Okay, when did we decide that we'll have our quiz, first quiz? Ayush?
It's tomorrow, right?
Huh? Tomorrow. Okay, good. I hope, okay, good that you didn't forget. Okay, so let me just quickly go over whatever we were doing in the last class. We started with Poisson process. Okay, so how did we define? So the first thing was, we defined what is a renewal process, right? So what is a renewal process? It's an arrival process for which the inter-arrival times are IID, right? For example, you understood what that means, right? So this is nothing but inter arrival times, or IID. This is called a renewal process. Okay. It has, well, Poisson, so this is a very general definition. Poisson process turns out to be a renewal process, but there are a few other things, right? For example, what I can do is I can take a dice, throw it, depending on what I get. For example, if I get 4, I'll ensure that after 4 slots, a new person will arrive. Okay, then again I'm going to throw the same dice. If the outcome turns out to be 2, I'll let the person come in after 2 time slots after 4, and so on. Okay, that is also a renewal process, but it's not a Poisson process, right? So this is something that we looked at in the last class. So constructing a renewal process is very easy that way. Then we looked at Poisson process, right? In fact, Poisson process is also a renewal process because the inter-arrival times are IID. But in Poisson process, the inter-arrival time, right? So inter-arrival time X is exponentially distributed. Okay. So in some sense, you have a clock. Okay, it will tick after an amount of time that is governed by exponential distribution. Okay, so how do you generate this Poisson process? So let's say you start at 0, then you start your Poisson clock. After some random times, according to exponential distribution, it will say tick. Then you assume that there is one person arrived there. Okay, so for example, you start here 0, and then it ticked here, and there is one person, the first person. Okay, and then again reset, then again run the exponential clock. After this, it will click, let's say here, then the second person will arrive here. Okay, then again you do that, third person will arrive here, and so on. Okay, if you look at this inter-arrival time, this is x1, this is x2, and so on. These are all IID because I'm going to sample from independently from exponential distribution. So they are independent and identically distributed. Therefore, Poisson process is a renewal process. Is that fine?
Sir, x1 will be 0 to 1, I think, no?
No, x1 can be anything, right? It can be from 0 to infinity.
This interval time, sir. x1 here in the picture you have written, sir.
It can be anything between 0 to infinity. There is a possibility that there is an arrival at, let's say, some time. Okay, t1. Let's say the first person arrived here. Then after a long time, the second person can arrive. Okay, this distance could be really large. Okay, let me call this as delta. Now, what is the probability that this delta is large? So essentially, suppose if I ask this question, right, this delta is nothing but the inter-arrival time. So x is greater than some very large number delta. This is nothing but delta to infinity, right? Right, delta to infinity, the exponential distribution, right? dx dx. This is the probability. So what happens to this probability? Lambda e power minus lambda x by minus lambda delta to infinity. Infinity is 0. Delta is, so this lambda cancels, e power minus lambda delta. You can see this, right? What can you infer from this? If delta becomes large, the probability that the inter-arrival time is large goes down exponentially to 0. That means if you take delta to be equal to 0.1, maybe the probability is quite high. But if you take delta to be 10, the probability is so low that most of the times you will observe another person arriving at the cube before 10th slot. Okay, 10 time slots, or t equal to delta equal to 10. Is that fine? Did you get this?
Yes, sir.
Okay, everyone? Okay, so
hello, sir.
Yes.
Sir, actually, this exponential, this interval time, it follows exponential distribution. So essentially, that means the interval time decreases between every 2 persons arriving.
No. So each time you are going to sample from exponential independently. That's why it's a renewal process, right?
Okay. Yeah.
See, at what time first person arrived has got nothing to do with what time the second person has arrived. But you have to keep the order. That's all. Okay.
Oh,
Think of it as like this. I'm going to throw a ball. Okay. So you're going to get the ball. So what I'm going to do is I'm going to draw a sample from exponential distribution. Okay. The first sample turned out to be 2.1. I'll wait for 2.1 second and throw the ball to you. So you get the first ball. Okay. Again, I'm going to sample from exponential distribution, independent of the previous. Maybe I'll get 3.1. So what will I do? 2.1 plus 3.1 is 5.2. So at 5.2 second, I'll throw the second ball. Okay. And so on. I repeat that. Okay. So I'll keep on getting balls at random times, but that turns out to be an exponential arrival of cricket balls, for example. Is that fine? But you have to ensure that the inter-arrival times are exponential and independent. Fine, right? Rishabh?
yes, sir. But sir, from one sample value, here I know that the sample values we are taking from exponential distribution. But if we see from the other point, from one sample, how can we say that it is collected from exponential distribution?
No. So, okay, let me tell you how to generate this, okay? Generating Poisson. Okay, arrival. Okay. So, what you do is you take, you know how to do this, right? What is this? What is the meaning of this? I'm sampling independently from a exponential distribution in an IID fashion. Fine. How many samples did I get? In fact, I'm going to call that function again and again and again. So I got infinitely many. So now, how am I going to construct the arrival process? So this is 0. This is x1. Okay. This is x2. This is x3. Sorry. This is x3. This is the third person. Fourth person, let's say he's here. This is x4 and so on. You understood, right?
Yes, sir.
In MATLAB, for example, if you want to approximate Poisson arrival, let's say you want to model some packets arriving, let's say 1 lakh packets arriving at a router, which is to be modeled as Poisson with rate lambda. What you do is you generate 1 lakh independent exponential samples drawn from exponential distribution. Then you just mark it like this, and this is the arrival instance. Okay.
Okay, sir.
Okay. So now, so we know what a Poisson distribution is, or Poisson arrival is, or Poisson process is. So there is one more thing called a memoryless property. Okay, so let's look at that. This is very important. I'll define it, and well, I can do the other way. So this arrival, Poisson arrival, turns out to be memoryless. Okay, but let's put that as a definition and show that Poisson arrival is memoryless. Okay, so memoryless random variables. So what is this? We say that a random variable x is memoryless. Okay, if first of all x is a positive random variable, okay, such that or for which we need to have the following. So probability of x greater than t plus x is equal to probability of x greater than x, probability of x greater than t. Well, when I said Poisson process, it's essentially what I'm referring to is your inter-arrival times. Okay, inter-arrival times for is memoryless. Okay, is this fine? So what is it saying intuitively? It's saying the probability that your inter-arrival time is more than t plus x. So let me draw that in terms of a picture. So this is your t, 0, and x is this much. This is your t plus x. Okay, you are asking the probability that the inter-arrival time, for example, the first person arriving is more than t plus x, is same as the probability that it's more than t times the probability that it's more than it's more than okay, t and times the probability that it's more than x. I think in the picture it's okay, let me just change the picture. This is x here. Okay, this is t plus x and this is t. Now this says the probability that x is greater than t plus x, it's somewhere here, as I said, is probability that x greater than x, that means it lies here, times the probability that x is greater than t, that means this thing. Okay, so now let's look at this property for exponential distribution, right? So if x is, let's say, distributed as e power minus lambda x, x greater than or equal to 0, probability of x greater than t plus x is what? We saw that earlier, right? So probability that x greater than delta is e power minus lambda delta. So this is nothing but e power minus lambda times t plus x. This is nothing but e power minus lambda times t times e power minus lambda times x. But what is this? The first one? E power minus lambda t is nothing but probability that x greater than t. E power minus lambda x is nothing but the probability of x greater than x. So it satisfies the property of memorylessness. Is that fine? Okay. So what is this saying? This is saying if I write this, so for example, let me rewrite this. Okay, so you consider this x greater than t plus x equal to probability of x greater than t times probability of x greater than x. Okay, this is what we have. So I can write this as probability of x greater than t, right, or x greater than x, for example, is probability of x greater than t plus x divided by probability of x greater than t. Do you agree? So this I can write it as probability of x greater than t plus x. If it's greater than t plus x, it should be greater than t also, right? So, and x greater than t. Well, this statement, this particular event is vacuous, because if x is greater than t plus x, it has to be greater than t, because we are dealing with positive quantities, right? So this is probability of x greater than t. What can you say about this term? What is this?
Conditional probability.
Conditional probability, right? So it says this is nothing but probability of x greater than t plus x given x greater than t. Okay, so that means conditioned on the event that x is greater than t, if I ask what is the probability that x is greater than t plus x, slightly more than t, that is same as x greater than x. That's what it says. Okay, in terms of pictures, you are looking at, for example, x here and t here. Okay, so you're asking what is the probability that x is greater than t plus x. That means it lies here. It lies here. Okay, the problem, given that x is greater than t, so let me just change that. Okay, so just to make sure, this is x is greater than t, so this is t and this is x. Okay, I'm asking, I'm conditioning on x greater than t. That means I'm saying it's lying somewhere here or whatever beyond t. Given that, I'm asking what is the probability that x is slightly more than t, that is more by x, right? T plus x. So I'm saying what is the probability that it lies here, given that it lies here, right? So in other words, given that it lies here, what is the probability that it lies here, right? Is this fine? Pictorially? I'll repeat. I'm saying that a person is going to arrive at random times beyond t, that is somewhere here. Okay, fine. So I'm conditioning on the fact that the person is arriving after t. But I'm asking what is the probability that he will arrive after this t plus x? Conditioned on the fact that he is arriving after this. Now it says that is nothing but probability of x greater than x. That means this duration is what matters. It's x is greater than x. That's what it depends on, right? It did not depend on what t is and what t plus x is, right? It depends on x only, the inter arrival time, right? The last time at which somebody arrived and the time of interest. That's what it depends on. It doesn't depend on when the last person arrived. Is that fine?
Yes, sir.
Okay, so this is yes.
Sir, this small x, the inter-arrival time, we can take it less also, sir.
No.
Suppose,
So x should be greater than 0.
No, sir, I am not saying that. Actually, sir, suppose I am interested in finding the number of people arriving after the suppose in particular eight arrival. After 8 arrival, number of people arriving. I am interested in finding the probability of that. And
Correct.
given that the fourth person has already come, sir. Like I am just enlarging
Okay,
this
I understood.
inter-arrival time.
You are saying, for example, okay, I'll write that. So you're saying you are at some time t, and no, let's say let's say that 4 people have already arrived. Okay, you are saying condition on the fact that 4 people have already arrived. What is the probability that this is some t plus delta? What is the probability that n people will arrive here, right? Conditioned on 4 people have already arrived. That's what you are asking?
No, sir. Actually, sir, you just said here that what is the probability that x is greater than t plus x, no, sir, and
Correct.
condition that x is greater than t.
Yes.
So this t, suppose this t is the last arrival. Sorry, second last arrival, you can say.
That is not conditioned on that, right? So I'm just looking at the okay, you can interpret this as inter-arrival. So you are saying from the last time when somebody arrived, the next person will arrive at least after t seconds, right? That is what I'm conditioning on. I'm asking what is the probability that the next person will arrive after t plus x.
Okay, sir.
Right? So it's like this. I mean, I can also extend this, right? So there was an arrival here. Okay, I don't know. This is some t. Okay. Now I'm saying this is my t. Okay, so let me use a different color. Okay, this is t, right? So there was some arrival at this point, and I'm saying the next person will arrive after t. That is the event that I'm conditioning on. Now I am asking what is the probability that somebody will arrive after t plus x? So this will be x, right? Somebody will arrive here conditioned on the fact that basically nobody arrived here. Okay. I'm saying that probability is same as the probability that this x is greater than this small x. Okay. It only depends on this duration. It doesn't depend on where you are asking this question. Right?
Hello, sir.
Yes, sir. Actually, sir, there will be no arriving between t and t plus x. No, sir.
Yes, that's the assumption. Yeah.
Okay, sir. Okay.
That's what it means.
Okay, sir.
Yes, Rishabh.
Sir, actually, we assume at the very first place that the interval times are IID, like it doesn't depend on one another. So, sir, does it follow from that fact, or is it only because of exponential?
No. It's because of exponential. In fact, if you want, I think one can prove that if you want memorylessness, then exponential is the only distribution. Okay. I think you can prove that. I have to check. Okay. So I have to check that. But I think you can prove that. Is that fine? It's not because of exponential, right? Sorry, it's not because of independent. Where have we used independence here? We have used only exponentials, right? This splits this way, and I can write it like this. It doesn't depend on independence. Is that fine?
Yes, sir.
Okay.
So actually, the statements were kind of same. Like IIDs also doesn't depend on each other. That's why I thought maybe.
No. So here it's not about across two arrivals. I'm talking about only about the same arrival, right? I'm saying somebody arrives after t, that is given, but I'm asking what is the probability that it arrives after x seconds from t? You understand, right?
Okay, sir. Okay, sir. Okay, sir. Now I
So
understood.
I'm going to say that it's going to rain sometime after tomorrow, but that is conditioning. So somebody has told you that it's going to rain after tomorrow. Okay, that is the condition given. But I want to know what is the probability that it will rain day after tomorrow, given that it will rain after tomorrow, right? So then that depends only on the duration between tomorrow and day after tomorrow. It doesn't depend on whether I'm asking about tomorrow or day after, whatever, right? So it only depends on the distance x, not on t, where exactly you are asking that question. Right?
Yes, sir. Yes, sir. Now I understand.
Okay.
Yeah.
So this is very important. That's why I thought I'll spend some time. Okay. So now let's ask another question. So okay, so some notation. So I'll finish that first. I think we looked at those notations. So the arrival time instance, I'm going to mark it as S1, S2, and so on, right? That's something that you saw in the last class also. S5, blah, 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 right? If you take, for example, T, the number of arrivals, right? N of T, the number of arrivals is denoted by N of T. In this case, it's 3, right? There were 3 arrivals, right? These are the two notations. Okay, we are going to prove an interesting theorem now. Instead of formally stating the theorem and proving it, let's ask this question and try to answer them. Once we answer them, we will write that as a theorem statement. Okay, so let's look at the following. Okay, now so let's look at this this picture. Okay, so let me write a picture here. This is 0, it starts at 0, and the first arrival happens somewhere here. Okay, this is the first arrival, S1. Okay, so the inter-arrival time is, of course, I can write this as first arrival, and there is a second arrival here, let's say, and it goes up like this and so on. So this is X1. Do you agree? This is the inter-arrival time because you started at 0, the first person arrived at S1, that is X1. So S1 is X1. Okay. Now let's look at some time T. Okay, this is your T. Okay. Now let me call this as Z. Okay. Is the picture clear?
Yes, sir.
S1 is the time instant at which the first person arrived. T is somewhere in between 0 and S1. So what can you say about N of T?
0, sir.
0.
Because nobody arrived, right? This is something. Okay. So now this is the question. So what can you say about probability that Z is greater than Z conditioned on N of T equal to 0? Remember, Z depends on T, right? It looks like Z is X1 minus T, right? So I can write that here. Z is X1, S1 minus TZ. Okay. So what can you say about this? So let's write this, right? So probability of Z greater than, Z is what? S1 minus T, right? Greater than Z given N of T equal to 0, right? So this is nothing but probability of, what is S1? S1 is same as X1, right? So this is same as X1. You agree? S2 is not same as X2, okay? This is same as X1 is greater than Z plus T given n of t equal to 0. Okay. So what can you say about this? So n of t equal to 0. So let me write this entire thing. Okay, so x1 greater than z plus t given. What can you say about n of t? So n of t equal to 0 essentially means that there is no one arriving, that nobody arrived before t, right? That's what it says. Or in other words, if I were to write this in terms of x1, right? Clearly this x1 is greater than t, right? If x1 is greater than t, definitely n of t equal to 0. If n of t equal to 0, then x1 has to be greater than t. Do you agree? Everyone agrees with this or no? Yes?
Yes, sir.
Yes? Okay. So now, what can you say about this?
Greater than z, z, small z, probably.
Yeah, right. So x1 greater than z, because x1 is greater than t, it's given. So this is, it turns out to be probability of x1 greater than z, which is nothing but e power minus lambda z, right? What do you infer from this? Essentially, this says that this is basically independent of t, right? It only depends on z, right? So if you look at this, z greater than z given n of t equal to 0, essentially it says that this only depends on z, not on t. So that means it is independent of the time instant at which you are asking this question, right? It only depends on how far. Z is what matters, not this small z is what matters, not not the time instant t. You agree?
So why did we bring the notion of z? Is it because we want to know after time instant till
Yes.
the next appearance
Arrival.
of?
Yeah. See, we started with no arrival, nobody arrived till t, and I am asking what happens in the future, right? Given that nobody arrived till time t, right? So that depends only on the future, not exactly on time t, right? That's what they're trying to say. Or so essentially, I can state this way. Okay, so roughly, this leads to the following theorem. Okay, so for a Poisson with rate lambda, any t greater than 0, the length of the interval from t until the first arrival after t is a positive random variable z with PD of this thing, right? So for a Poisson for a Poisson process with rate lambda, for every t greater than 0, the interval, what interval? Interval from t until the first arrival, right? X1 is that, right? So the first arrival is a positive random variable z with, see, this complementary CDF is e power minus lambda z. What is the CDF? CDF would be 1 minus e power minus lambda z. Okay, this is what it says. Is this fine? Is this fine?
Hello, sir. Can you take the diagram like where you drew the x1, z, and that?
I'm saying this distance, right, from t till the first arrival, this is distributed as 1 minus e power minus lambda z.
Sir, here in the diagram, can we see small z here? Like.
So this is the random variable z. The instantiation is small z. Okay.
Sir, but
I'm asking what is the
x1 we
probability
take
that,
from sir, x1 we initiated from 0 and by writing x1 is greater than z.
So it's like this. Okay, I think I should give some more MATLAB exercise, I think. So you do the following, okay? You generate random variable x1 according to exponential, okay? Okay, this will tell me the first arrival, right? Let me call this as x11. You generate another x12 exponential, okay? And so on. You do so many things, right? Each time, so this is x1, okay? This turns out to be x1. Do you agree? Again, I can start from 0. This turned out to be s1 now, which is x1 1. This is x1 2. Then again, this turned out to be s1, which is x1 3, and so on. Okay, is this fine? You got all these, right? There will be many diagrams that I can write. In other words, I'm generating some n number of parallel, n number of Poisson arrivals. I'll stop the moment somebody arrives. That's all. Okay. So what is x1 in this case? X1 is this one, right? The whole thing, right? Okay. Now fix a t. Okay, any t that you want, right? Maybe just for the sake of simplicity, I'll okay. Let me not even do that. I'll fix a t. Okay, so t is what? Let's say somewhere here. Okay, this is my t. Fine. Now, what is z here? This is z, right? What is z here? This is z. What is z here? Negative, right? So in fact, less than 0 here, right? Okay. Do you agree?
Yes, sir.
Okay. So that means I have to basically discard this because this arrival doesn't count. I mean, I'm saying I should consider all those arrivals where t is within the first arrival. Okay. Because that's how
Already
I'm
arrived,
choosing yeah. So I'm choosing t like that. Now, what is z greater than z? For example, z is, let's say this is 0.1. Okay, this z turned out to be 0.2, this turned out to be 0.9, and so on. So I have to count whenever z is greater than 0.1. I have to count this, I have to count this, and so on. Some of them I don't count, right? Whenever I count, I add all of them and divide by n. That is the probability that z is greater than z, right? That probability is given by e power minus lambda z is what this particular theorem is saying, right? Well, you cannot just do n experiments, but you have to do infinitely many experiments like this. Okay.
Yes, sir. But sir, in the expression we wrote x1 greater than small z. That's why I had this confusion.
No, that is equal to this, right? So that's why this is equal to this.
Yes. Okay.
It's an equality, right?
Yes,
Okay.
Yes, sir. Yes, sir.
Yeah. Let's move on to the next one now. What is the next one? So let's suppose. Okay. So let's look at this. Suppose I say n of t equal to n. What do you mean by that? At time instant t, n people have arrived at the counter, or n packets have arrived at the router, right? Is that fine? If I say Sn equal to tau, what does that mean?
Tau is less than n. Sorry, tau is less than t.
Tau is less than t. No, that's correct. Yes, but what is Sn? Sn is the time instant at which the nth person arrived, right? So if I say Sn equal to tau, tau is the instant at which the nth person arrived, right? Is that fine?
Yes, sir.
Okay. Okay. Right. Now I ask, let's look at this. Let's look at this probability of z. Okay, I have to define what z is. Okay, which maybe I'll do that first. I'll do it pictorially. Okay, you have to define it mathematically later on. Okay, so there is okay, so here is the time instant at which the n-1 person arrived. Okay, 1 second, man. Hopefully, hey, just give me a minute, give me 1 minute, okay? I have to go, something urgent. ಕ್ಲಾಸ್ ಇದೆ ಈಗ ನಮ್ಮ ಕ್ಲಾಸ್ ಮುಗಿಸ್ಕೊಂಡು hello, yeah, I'm back. So Sn minus 1 is nothing but the time instant at which n plus n minus 1th person arrived. Let's look at Sn, which is basically tau in this case. This is the time instant at which the nth person arrived. Okay, if n of t is n, that means I'm considering t somewhere here, right? This is my t. Okay, is this fine? Maybe I'll use a different color. Okay, so this is t. This is my t, because n of t is n, therefore definitely t should be greater than tau. I will put a horizontal line after tau. Okay, now what is z? Let's define z to be the arrival time after this time t. Okay, so somebody would have arrived after this, right? So let's define that to be z. Okay, okay, is this fine? So what does that mean? Somewhere something like this, right? So somebody arrived here, it jumped, right? Jumped up and stays constant, and let's say somebody arrived here. Okay, so this is something like Sn plus 1. Okay, and it will jump even further. Okay, so I'm going to pick my t in such a way that it's before the next arrival but after the nth arrival. Is that fine? So I will define my z as this. Definitely this z is random, because each time you conduct the experiment, you will get different numbers for z. Is that fine?
Yes, actually we are just shifting this small t. Initially we have done for the 0 to first arrival,
exactly.
And now we are taking to any interval.
Yeah, so S0 is what we started. S0 is equal to 0 is what we started. Now we are shifting it to a general nth arrival. Okay,
Yes.
and asking the same. So what is the question that I should ask now? Probability, in terms of probability z greater than z, given what? N of t equal to n, that means there are n arrivals, that is t is after tau, that is Sn, and Sn equal to tau, right? So this is what the question that I would like to ask and answer, right? So what can you say about z now? What is z? Okay, now the trick is I have to write everything in terms of inter arrivals, right? I cannot, I think I mentioned that in the last class, it's very hard to deal with the instant at which the arrival happened. It's always easier to deal with the inter arrival times because it's nice exponential function. Okay? Is that fine?
Yes, sir.
Okay. Now, how do you write this z?
xn plus 1 minus t.
Xn
plus 1 minus t.
So summation of xn.
This is xn plus 1. Okay.
Yes, summation. We have to sum up all t until xn plus 1.
I think we can write it in terms of whatever he is saying, right? So this z is nothing but xn plus 1 right? Or I can write this xn plus 1 as what? As this small z plus, okay, so this is z plus this thing. What is this? T minus tau, right? Tau is this, t is this, t minus tau. This t minus tau, right? Is that fine from picture?
Yes, sir. Yes, sir.
So probability of z is nothing but xn plus 1 and xn plus 1. Okay, what
minus
did I
t
do?
plus tau.
Xn, so z is xn plus 1 minus t plus tau, right? Minus t plus tau is greater than z, conditioned on all this, right? I can write this as probability of xn plus 1 greater than z plus t minus tau given these things. Okay. Now, what can I say about this now? So I'll write it as is xn plus 1 greater than z plus t minus tau, conditioned on, if I say n of t equal to n, what does that mean? At the tth time instant, you only have n.
N number of pupils.
Till this point, there was n, right? If at all there was an arrival, it was after t, right? So now that essentially means that the inter-arrival time, right, xn plus 1, this one, it should be greater than t minus tau, right? It should be more than this interval. Do you agree? So that means I can write this as xn plus 1 is greater than t minus tau and Sn equal to tau. Do you agree with this?
Yes, sir.
Okay. Now, the next step would be, so somehow I have to get rid of this, right? So what is this saying? This is saying the nth arrival happened at tau, right? But I'm saying n plus 1th arrival happens after t minus tau, right? This is the duration, right? So now this is clearly the xn plus 1th event is independent of what happened at the nth arrival, right? Sn equal to tau. So I can write this as xn plus 1 greater than t minus tau. It's independent, right? Is that fine? Xn plus 1 is independent of Sn, right? Do you agree? Do you agree? How are you generating xn plus 1? Hello?
Sir, tau is involved in xn plus 1. So,
No, how are you generating xn plus 1? What information do you need? So we'll go back to Poisson arrival. How did we generate Poisson arrival? That's why I think it's a good idea to write the generation process, right? Generating Poisson arrival. How did we generate xn plus 1? Somewhere down here, there is xn plus 1, right? How did we generate? We sampled it from exponential distribution. That's all. Independent of everything, right? Before even independent of everything, we generated this. Do you agree?
yes, sir.
So it doesn't depend on when the previous thing arrived. I mean, it only depends on, it's independent of everything, right? Do you agree?
Okay,
So
sir.
it's obviously independent of Sn also.
Yes, sir.
Now what is the next step? What is the next step? Xn plus 1 is greater than t minus tau. Exactly, right? Memberless. So what is it that I have to do? Xn plus 1 is greater than z, which is e power minus lambda z. Nice, right? Right?
Sir, one thing I didn't understand. Sir, can you just scroll down a bit? Like when you started this, sir, just a bit. Sir, yes, sir. Sir, Sn means the moment, the time when nth person arrives, right?
Correct.
That means n people already arrived at at the
Correct.
time instant
Correct.
sn.
Correct.
And sir, nt is like the number of person arrived, that is equal to n, the
That is
total
true.
count.
Correct. That means nobody arrived after tau till t. That's what it's saying. At tau, somebody arrived, but after tau till t, nobody arrived for sure. Now we are asking how much time does it take, or what is the distribution of the random variable z, right? How much time does it take for another person to arrive after t? Yeah.
Okay, sir. So that means before deriving this, the previous derivation was like for the first arrival, that
Exactly.
case, and
That's
now
what
we are for
Sumit was
generalizing.
mentioning. Yeah, Sumit was mentioning, right? You are just
Yes.
shifting it. That's what you're doing.
Okay.
Okay. Is that fine? Any questions regarding this?
No, sir, it's fine.
Okay. Okay. Let's move on. Okay. So what does this result in? This results in another theorem, which I can state as follows. Again, blah blah blah. So whatever we need, it's a Poisson arrival on that. So this random variable z, right, is independent of what? Independent of what? N of t equal to n. That's what it says. It depends on independent of n of t, right? And the n of t arrival epochs, right? And the n of t arrival epochs before what? Before t, right? That's what it says. Okay, and it's also independent of all the arrival before time t. I mean, n of t, the counting process before time t. It is independent of that. Okay, so just take a refer book. This is what for the precise statement. Okay, essentially this is what we have proved. Okay, so there is another interesting thing called counting process. Okay, so what is counting process? We have been looking at this. In fact, what is a counting process? N of t, right? This is a counting process. So a counting process n of t such that t is greater than 0. This has the stationary increment property. I'll write this and explain. If n of t dash minus n of t, okay, t dash is obviously greater than t, has the same CDF as n of t dash minus t for all t dash greater than 0. Okay, this is what, well, t dash should be greater than t greater than 0. Okay, you understand what this says? So, okay, let me write this. This is your t and this is your t dash. What is n of t minus n of t dash?
So number of people
arrive
at a time t.
Exactly.
Yeah.
Between this, right? Between t
Yes,
and t dash, right? So now the number of people arriving in this window is a random variable, right? It gives me the count. It's a random variable. Now what this says is this has a distribution, right? It says this distribution is same as n of t dash minus t. What does that mean? Huh?
So same
So
thing.
any t dash minus t interval. Yeah.
Yeah, right. So that means it's same as, for example, you start at 0 and you take t dash minus t here. Okay, how many people arrived here? Right, that random variable and this random variable have the same distribution. So in other words, it doesn't depend on t and t dash, rather it depends on the difference delta. That's what it's saying, right? It's called stationary increment, right? This is the increment, but it is stationary. It doesn't matter where you look at. You move this window, delta window, anywhere. The number of arrivals in that window distribution is same. Okay? That's what it says. Is that fine?
Yes, sir.
Okay. I think I'll stop here. In the next class, we will look at few other things, and then that will sort of complete the Poisson process description. There are other alternate description for Poisson, and we will look at a few properties of Poisson. I'll decide on whether to look at properties and come back to other descriptions of Poisson, or complete that and go to properties. Okay. So tomorrow at 11, right? Hello.
Yes, sir.
11.
Date,
Okay.
sir. Today my classes one two also. So they. Hello.
Yes. Yes.
One subject also Q's tomorrow.
Okay.
So date tomorrow means 14, 15 any day.
No, I didn't understand. What is your concern?
Sir, means 13 October. One. Hello.
Okay. Yeah. Go ahead. Hello. Please
Sir.
go ahead.
Hello.
Please go ahead. Tell me.
Q is extended, sir. Please.
Why?
14 year 15 day. 15 year 14 October.
Why?
Because tomorrow my one Q also discrete structure. So
this is for 24 hours. You can sit overnight and do it. No problem. No, I'm not going to change the quiz. Okay.
Okay.
See,
Okay.
you cannot. You cannot give excuses like this. If you have like 4 quizzes on the same day, then you can say, well, 5th quiz you please shift it. I mean, just another quiz and also 24 hours collaboration based. I mean, what else you need?
Hello, sir.
Yes.
Sir, I mean, this week we are having quizzes of different subjects. So, in the calendar mentioned in the website, so the midsem, when will be the midsem?
Midsem week is what 2 weeks from now, but I'll push my midsem a little late. This
So
is
that
grad
will be
level
good, yeah.
PhD, so I'll push my midsem a little late. Okay.
So that's both for this subject and data science also.
No, data science. Yeah, sort of. I have to push that data science as well.
Okay, sir.
Yes.
Okay. Sir.
Yeah. I'll push it by 1 week. Okay.
Hello.
Yes.
Sir, this for the collaboration thing, the partner of the group will be decided at 11 a.m. or we can choose it on our own.
No. I will write on the question paper. You will know. Savan, you have the list of students and their email IDs, right? Of this course. Okay. So quiz, I'll do one thing. I'll give it at some time tomorrow after 11. Okay. So maybe at 2 or 3, but I'll give you 24 hours time to collaborate. Is that fine?
Okay, sir.
Okay. Yeah. May not be exactly at 11, but I might, depending on the schedule tomorrow, sometime, but I'll give 24 hours time with all the details in the question paper. Okay. Yeah.
Okay, sir.
Yeah.
Sir, per team there will be 2 members, sir, or
you'll get to know tomorrow. No, why? How does it matter?
Okay.
So ideally, you should know the answer and you should write it and maybe discuss with others also. That would be great. Okay. There will be questions like that also. Okay. It's not like everything you discuss. Okay,
Okay.
there will be questions that that you have to answer on your own.
Okay.
Okay, yeah. Okay, okay, then I'll stop here. Savan, can you please stay back? Others can leave.
Yes.
Okay, thank you, sir.
Yeah, thank